So in this video, I'll explain how to complete problem 6 from the chapter 3 homework. So this problem says to consider the 4 scenarios involving visible light. I'm only going to demonstrate one. You can use this video to help guide you through the other 3. I don't want to just give away the answers. I want to still make sure that you're able to apply the concepts that are being discussed, but I do want to help you to make sure that you're able to apply those concepts. So again, it says to consider the 4 scenarios involving visible light. So the fact that we're dealing with visible lights gives you a clue as to what type of electromagnetic radiation. Why that's important is because it gives you insight into the possible values for your wavelength as well as your frequency. So if you recall from the electromagnetic spectrum, and I'll just go ahead and show that, you have different wavelengths and different frequencies for the different types of electromagnetic radiation, and visible light falls within this small region. It's actually expanded out to show you those different colors, but it's somewhere around that 10 to the minus 7 meters area of the spectrum. So that's important because we know that if we're dealing with a wavelength that is 10 to the third or 10 to the minus 12, we know that we're not dealing with visible light. But because we are dealing with visible light, we know the general area of this spectrum. Since I have this up, I'll go ahead and complete a portion of this problem, because let me read it first. In scenario A, visible light has a wavelength of 726.3 nanometers. Determine its frequency, energy per photon, and color. So we don't have to do any calculation in order to determine the color. You were already provided with the wavelength. And so if you look at that wavelength, 726.3 nanometers, if you notice the portion of the visible region that is expanded, so at the very bottom, the colors of the rainbow, just locate the general area of 726.3. And so we see 700. So of course, 726.3 will be somewhere to the right. This scale is going from 700 to 750. So we're looking somewhere in the middle. So somewhere within that region. So just indicate what color that represents. And that's how you would answer the visible light in scenario A is. It's a drop box that has different color options. So you'll just select the color option that applies to. Now for the frequency and the energy, we're going to have to actually do calculations. And so keep in mind, again, dealing with visible light, frequency, we have the wavelength. We're trying to find the frequency. So then you want to ask yourself, is there a relationship between the two? You have energy that we're trying to calculate. Again, we're given the wavelength. Ask yourself, is there a relationship between those two? It doesn't matter which one you solve first. You can solve the frequency first and then the energy. You can do the energy and then the frequency. The order doesn't matter. So I'm going to start with the frequency. And so keep in mind, because we are looking at a relationship between frequency and wavelength, that indicates which equation we should be using. And that's going to be the C equals lambda nu equation. So remember, C is the speed of light, lambda is our wavelength, and nu is the frequency. Also keep in mind what units have to be used when using this equation. The speed of light is given in the units of meters per second. Frequency is measured in hertz, and remember, hertz is an inverse second. We can also show it as 1/second. So that means that our wavelength has to be in meters to use this equation. But if we notice, our wavelength is not in meters, it's in nanometers. So that means that before we can use this equation, we have to do a conversion. So that's where we're needing to start. So if our wavelength is shown as 726.3 nanometers, we have to convert it to meters first. So ask yourself, is there a direct relationship between the meter and the nanometer? And there is. For every 10 to the minus 9 meters, that's the same as 1 nanometers. So that causes my nanometers to cancel out to leave me with meters. So if you put this in your calculator, you're going to get 7.263 times 10 to the minus 7 meters. So now that we have that wavelength in meters, now we can actually go and solve this equation. So again, C equals lambda nu. So we can either go ahead and rearrange this equation now, or we can plug everything and then rearrange it. Either way. But we need to solve for the frequency, which is nu. And so we need it by itself. Right now we have that times the wavelength. So the opposite is to divide by the wavelength. When I divide one side, I have to do the same thing to the other side. On the right side, they cancel out. On the left side, it leaves me with C over lambda. So I'm just going to switch the order. I'm going to just show my nu here, and then my C over lambda. And then we can just plug in those values. So you have your speed of light. Again, that's a constant value. Oops, not minus 8, 10 to the 8th meters per second, divided by our wavelength, which we just converted to meters. And then once you put this in your calculator, you'll get your answer in hertz. So hopefully you're able to put that in your calculator to get your value. Again, my recommendation is that you practice with it just to make sure that you are able to calculate using scientific notation, especially since we're dealing with two different numbers. I'll go ahead and fill in the blank for this one. Once you put it in your calculator, you should get 4.13 times 10 to the 14. So that's how many hertz. So that's your frequency. And so, and actually I should have went, if we're doing significant figures, I should have actually showed it as 4.128 because our measurement had 4 significant figures. So 4.128 times 10 to the 14 hertz is based on the rules of significant figures. So that's your frequency. So now you have your frequency, you have the color of your visible light, but now we have to figure out the energy. And so with the energy, when we're dealing with the photon, remember photons are like sample sizes. We can think of it that way. So there's set amounts of these particles, set amounts of these different types of electromagnetic radiation. The energy of a photon can be determined using Planck's equation. E equals h nu. So the energy is equal to Planck's constant times the frequency. And so since we already solved for the frequency, we can simply plug that value in. So we can solve for E. Planck's constant is always 6.626 times 10 to the minus 34 joules times seconds. And we just determined that our frequency was 4.128 times 10 to the 14th hertz. And so once you put those two values in your calculator, you'll then have the energy of the photon. And based on these values, when we do that, that turns out to be 2.735 times 10 to the negative 19 joules. So that's our energy. But let's say you decided to do the energy first and you didn't know the frequency. Now, clearly we just calculated it, but if you did the energy first and only knew the wavelength, because we know, I apologize for that, but because we know the equation E equals h nu, and we know the equation C equals lambda nu, if we didn't know the frequency, we do know that there is a relationship between the wavelength and the frequency. As we saw earlier in this video, if we rearrange this second equation, it turns out that frequency is equal to C over lambda, so the speed of light divided by the wavelength. And so I can actually substitute that in place of that nu symbol. And so I would have had the equation E equals hc over lambda. And so I would have used Planck's constant, 6.626 times 10 to the minus 34 joules times seconds. I would have had my speed of light, 2.998 times 10 to the 8 meters per second. I would have had my wavelength, which we determined after we converted to meters, was 7.263 times 10 to the minus 7 meters. And so once you have all of your constants, you have your wavelength converted to the correct unit, Multiply everything in your numerator, so Planck's constant times the speed of light, divided by your denominator, which is simply your wavelength converted to meters. Once you do that, you end up with an energy that is equivalent to 2.735 times 10 to the minus 19 joules. So if you notice, it's the same thing that we have using the opposite equation. So whichever equation you decide to use, you're still going to get the correct answer. So again, depending on what you're looking for and what information you're given, that will determine how you set up that problem. So I hope this helps.